So in this particular talk, we'll be basically taking a case study of a couple of our platforms that we have been able to scale by leveraging Aerospike, making it cost effective, as well as making it quite efficient to run at scale. The agenda for this particular discussion or this talk would be covering two of our platforms, uh, going a bit deep into it, like how did we go about it. And one of them is central entity attribute store, which covered first. And if the time permits, we'll go to the stream processing platform. So what is central entity attribute store? Basically, it is a single platform where we can define an entity and store an attribute against the entity. What is an entity? It's any distinct object or any concept within an organization, like a user ID, could be phone number, could be device ID, or any entity that you want to capture attributes against. And the attributes are defined as properties of characteristic of that particular entity. Why we need that? Because we are using this store to power multiple use cases, like campaign targeting. We are also helping out with feature rollouts or product rollouts, user experience optimizations, like which particular set of users having which particular characteristics can look at what part of user experience. Also driving experimentation, controlling cohorts, which experiment runs on which particular user set. Also marking or helping out fraud prevention to define certain attributes that are powered through the fraud system that mark user to be high, little high confidence on that the particular user is doing some fraud. What are the tenets of the platform? We wanted to have a single platform where multiple line of businesses, CRED being has a multiple line of businesses, like we have insurance, we have CRED Pay, we have payments, we have cash, CRED Cash. All of those wants to define their own attributes against a user so that they can control their own systems, they can give the right experience to the user based on this. And this allows us to store all of those attributes in a single place, where maybe some attribute which is defined by fraud system can be used by transaction system in real time to stop a particular transaction which could be fraudulent. And the other aspect of tenet, the other tenet would be to run this at a scale, making it horizontally scalable, extensible, making it easier to onboard a new attribute, making it easier to onboard a new entity. So what, on a high level, how does this entire platform looks like? That we have a line of businesses, services that are pushing data in real time. We have a platform, Kafka, which listens to these events. The platform has three components. One is a central deployer, which houses the business logic of how do they extract a characteristic for a particular user or entity based on what input events are coming in. This is multi-tenant. We have all line of businesses having their own namespaces. Each namespace has multiple attributes, and all the logic goes into this entity deployer, which writes these attributes to entity store, which is backed by, at the time it was backed by DDB and DAX. And same, because this is in real time, the LOB services, what they write, they can read in real time. We took a conscious call of not making it, we're not making or taking a guarantee that we will make it in session. The reason being that it is very difficult to do that, and also don't want to build use cases which are not supposed to be built on this platform. Basically, this is for low change or slow changing attributes. What are the challenges that we faced in this particular design was that our write latencies were quite high, and the cost of running this platform was coming majorly from the data store that we're using, which was DAX plus DDB, contributing to 50% of the platform cost. So why did we choose Aerospike? The first and foremost thing, it fits the query pattern. So what we wanted out of a data store, Aerospike was fitting into that. It was giving us fast read writes on a key value pair, and we could write our own data types as on the values. We can define that based on our use case. And that's where it started, because if it doesn't fit our query pattern, there is no point in evaluating this particular data store. It was giving us high performance at scale, low latency, scalability. It was very cost efficient, as we will see in the next few slides. Highly available, we were running it across AZs. Compatible with our existing data model, fits right well. Good library support across major languages. Future-proof, you can extend this horizontally. Data models are flexible. You can keep adding more kind of data models into new bins, and you can keep growing your platform on top of it. The migration from database, from DDB to Aerospike was actually very crucial, because this is a T0 system in our organization. If I give you, I'll not say that it's a wrong statement, but if this platform goes down, the app stops working, because the home page renders through characteristics of an user based out of this store. So it's a T0 store, and for the migration, we didn't want to have any downtime. We also wanted to have data consistencies, because we didn't want a user to have a particular experience, and the next time he opens app has a different experience, because there is a consistency issue between the two data stores, or when we do migration. Also, we wanted to do easily rollback, because again, can't have downtime. If anything goes wrong, we should be able to go back and restate the original state of the platform. Also, we wanted to do phased rollouts, where we wanted to sort of, let's say, move reads first, and then when it scales, everything is working, then we go to the writes, because moving reads is a little easier. You can do fallback much faster, but doing writes is a little tricky. And we also wanted to have minimal overhead to doing this migration. So what we did, we added 2 phases. One was at the write time, and one was the read time. At the write time, we actually created 2 sets in Aerospike. One is which corresponds to the original data. The other one was which was capturing the state of an entity. Is that entity migrated to Aerospike or not? So we were doing this via dual write, where we checked if the entity has migrated. If not migrated, then pull the original value from DDB, massage it, make the model changes, and write it to entity store. This was not enough, because our read to write is 10:1. So not all attributes or not all entities will get updated, and will take a lot of time for us to migrate out of DDB to Aerospike. So what we also did was that we did read repairs. And when entity was queried, we will fetch, we will actually look at if it is migrated or not. Not migrated, again, same thing. We'll pull the data, massage, and write back to Aerospike. So we basically broke down into multiple milestones for this, so that we can easily track it, manage it, and have SOP plans for fallbacks, so that there is no downtime and there is no degradation in the user experience. So we enabled dual writes and read repairs. We did a phased rollout of read first, and once we were able to see that the reads are scaling up, the system is working fine, we actually did write migration also to the Aerospike, and we marked the migration complete for the hot store path, or the hot path. The next thing was that we also migrated our ingestion job from database DDB to Aerospike, because now all writes are going to Aerospike, and it has the later context. And once everything was done, we switched off the dual writes, and the DDB was decommissioned from the platform. What it gave us was almost 55% reduction in cost right out of the box doing this migration. The major uplift that we actually saw was in our write time latencies and also in the read time latencies. So this was just by doing a well-crafted migration plan with a write SOP in place, without any downtime, we were able to achieve this with these kind of benefits out of the box. But can we do better? What next? Can we drill down further and look at where are we still, are there any scope of avenues where we can save cost further. So this was our initial topology of Aerospike cluster. We had one primary cluster on AZ first, or AZ availability zone A. Basically, that was the primary cluster. All read-write were happening into that cluster. And then we had two other clusters in other availability zones for replication. Like if the AZ goes down, then we should have data in other AZs. And that was through XDR. So my application nodes were spread across 3 AZs, and all 3 application nodes were communicating to the same one AZ. Can anybody guess like where is something which we can do to save a furthermore cost here? Okay. Yeah. So that's exactly what we did. But why we did that was because also looking at our query patterns, right? So our write to read was 1:10. That we were doing a lot of reads. And our read payloads were quite heavy because the write would happen from one event to one namespace, but the read can happen to multiple namespaces. Like it can fetch a lot of data. And that was also happening. And because of that, our inter-AZ byte costs were high. So to remedy, like to put, like how do we solve this? Like we make reads AZ aware, writes can go cross AZs. We don't care much because the scale is not much. And in previous slide, we also see that we were maintaining 3 different clusters, which is additional cost on maintaining those 2 nodes in other 2 AZs, which were just serving as a shadow clusters for maintaining the application across AZs. So we did this, right? We created a single cluster, which spread across AZs, have nodes spread across AZs. We chose Aerospike, its cluster replication to do cross-AZ replication instead of XDRs. And it basically gave us AZ local reads, which is 10x of writes, and writes are still cross-AZs, which is, again, we are good to have that cost on our platform. Similar kind of a migration strategy. We made changes in our client setup. The services were able to fetch what AZ they were part of. Aerospike was set up according to the rack awareness. The clients were set up accordingly. And we did the same thing. We bootstrapped another cluster. Once we bootstrapped another cluster, this time we did the migration or the bootstrapping through XDR. So when the new cluster came up, it came up with all the keys. For the migration, what we did here was that we switched off the write for some time and then switched all the reads and writes. So it was pretty straightforward. What this gave us was another 50% reduction in running Aerospike on our platform. 40% of that cost came from the nodes itself because we reduced the other 2 shadow clusters, which are other AZs, and the other 55% reduction came from the AZ network cost. So in total, 50% cost was saved on running this cluster. In totality of this exercise, final cost saved was around 75%. So let's say I was paying $100 to run this platform on DDB. Now I'm paying $25. And this was done in 2 phases, and that's what we were able to leverage Aerospike for. 75% cost saving, write latency reduced by 30%, and read latency reduced by 88%. The implication of read latency reducing by 88% is that our experimentation runs on top of this because we control the exposure and the targeting cohorts through this platform. And we could not run multiple experiments at the same time because it will the experimentation platform will read many times on user attribute store. And because of the latencies, we could only span up to some amount of experiments. But with this, our experimentation platform also could scale because this was becoming one of the bottlenecks. And in the experimentation platform itself, we were able to reduce the latency by 50%. So it had second order effect on the entire ecosystem. The other use case that I wanted to cover as part of this particular platform was segment reach calculation. We also power segments through this. Of course, the attributes are used as the characteristics of the user, which can be used to target, but there are certain logic which analytics and the growth team wanted to particularly specifically target. So we have segments also in place, which are statically defined or could be recurring based on a query on Databricks or on EMR. The use case was, for this particular thing, was that we'd run a lot of campaigns on our platform for growth, for merchant rewards and other stuff. And while doing that, ops always come and configure a segment with this kind of expression. Segment, I want to target user who was part of segment A and B and not in C. The problem often comes is that people are not able to see what is the reaches. And when they're configuring the campaign, more often times they sort of create an expression which actually targets only 1,000 users, and they have a budget of maybe lakhs. And which basically gives and this basically like the campaign performance is basically does not come out, and it takes time for them to figure this out and then fix it. So it takes a lot of time to get this out. So can we do better here? Can we get sub-second results so that whenever a campaign op is trying to do this, they can get the reach calculation? It's going to be a low throughput query, but we are also good with a 5% error rate. It's okay if it's 95% accurate because I'm getting sub-second results. Can we also solve this out as a problem? So why can't what is the problem with the existing data model? So existing data model is entity ID or user ID to a list of attributes or list of segments. Running this expression would mean that I have to scan all through the data and run this expression for each query, which is not scalable. It's not fast. It is backed by, it has to run on a batch platform or on a Databricks or on some other lakehouse. And also want to maintain a 5% error rate with complex aggregation or complex expressions. Same approaches, run a batch query, user to list segment for each expression, which will run on lakehouse latent, can't be solved within the campaign flow itself. Can we run it faster? Yes, we can run it faster. There are few approaches that could be taken, data sketches being one of the prevalent ones. But in our particular platform, we have a capability where people can also remove users from the segments. So we cannot use data sketches right out of the box. We have to make a little bit of tinkering. The other thing that we thought of was doing was using bitmaps, because the size of the cohort is not very high from the CRED context. The number of cohorts are also limited. Like we can mark them like maybe max 1,000 cohorts. So bitmap became one of the choices to make it fast, make it cost effective, and because they are little expensive in space from data sketches, but they provide us capability of removing users from the segments. So that's what we did exactly. We basically, whenever a segment is materialized, instead of materializing user to segment, or not instead, but along with user to segment, we also do segment to a list of users, which is nothing but a bitmap of users. And we apply that onto Aerospike because we have a capability where the users can move out of segment in real time also, apart from batch. So putting into Aerospike provides the bitmap operations where we can do set, unset a bit, and this was really helpful for us. For the read time, we actually can load the relevant segments which are part of the expression query and do the set operations in memory, which scales for our low throughput system. This was the final thing that we are deploying right now, where we have a batch pipeline which basically takes the segment definition, converts it into a segment to a bitmap kind of a structure, writes it into an S3, and sends the location into the cluster, into the Kafka, where the platform listens to that particular what new file has come out, because the file could be around 6 MB for almost 50 million users max to max. So didn't make sense to put all of that data into Kafka. So we publish into S3, where the deployers reads that particular what new update has come and writes that into the Aerospike again as a bitmap data model. So going back, so doing this, what it gave us is exactly what we needed, where whenever a campaign is created, somebody comes and selects a particular segments that I want to run this expression. Right now with Bitmap, we can actually give 100% accuracy with the second of latency. And this should solve for a lot of our misconfiguration of the campaign ops and give better understanding of what the user is trying to target and better performance on the campaigns and less error prone. So these are the few things that we did on this platform to solve few of our use cases, making it cost effective, leveraging Aerospike for what it provides well. And we were able to build all of this on this platform by basically just extending what we already had. So going, like that was all for the central entity attribute store. Now going to the next platform, which we also maintain in the data platform team, is stream processing platform. I am pretty sure a lot of you guys would have this kind of platform in your own organization. Similar, I believe that I've seen a lot of other talks where everybody sort of follows a similar kind of a layer, where we have a execution environment which is pluggable. Then we have a core execution model where we maintain lifecycle deployment, resource management, and then there is a pipeline module which basically manages governance, who can do what, bit of a control plane on what, starting and deploying a pipeline. Artifact management, like if you have a custom jar to be deployed along with it and doing that management. And then there are other layers which run across all three layers. I will take a use case which is of running promotions on CRED app, where promotions is basically we want to give us particular kind of a reward to the end user based because a certain brand wants to reward a particular user for their behavior, good financial behavior. So the earlier before we had the platform, this was the architecture where there was a serving system and we had an ingestion system which listens to the events. So whatever content that we show to the end user, the user interacted with it, that events came into ingestion platform, which came to data lake, where we did calculate feedback signals on like what is CTR on particular content, what is like how much user is sort of engaging with the content, so that we can figure out is that the content working or should we change the pitch to the end user. The problem with that thing was that because the feedback signals were running on batch, so the insight into how the content is doing was little delayed, and which basically made it a lot difficult to run these campaigns with the right set without doing overburn, without basically implementing a frequency cap so that the user sees fresh content and any kind of real-time relevance that you wanted to do. So we thought that, okay, let's use this platform and complement our batch jobs with a real-time counterpart, which can do this much fast in real time. So that's we wanted to. That's what we went ahead and did it. Where the serving events, serving events would log most of the metadata related to what was served to the end user. It will have a particular ID which would be specific to that particular instance of that content served to that end user. When the user interacts with that content, the events are generated with the same ID, which comes back to the backend. And we basically use that particular ID to enrich these events with the metadata that was captured at the time of serving serving the content. So yeah, this was the batch processing. We just introduced a stream processing job for doing this. How we can do this is because in sorry, I just sort of skipped a few slides. I think, yeah. So the problem which actually we wanted to discuss in this particular session was that doing a join in batch is like everyone does, but doing it in streams, where my stream join context window can go up to days. It's not trivial, right? You have to specifically solve for it, and that's what we actually did solve in the upcoming slides that we'll talk about. So what were the possible approaches of doing real-time stream joins? One is like using native Flink, because the entire platform is on Flink, the stream processing, and using native stream joins. RocksDB managed state store, off heap, it is fault tolerant, works. The only problem is that it works well. I would not say it works well, but I think I would be more comfortable running a join which only runs for a smaller time window on native windowed operations on Flink. Because our use case is that because the events can be late arriving, the clicks can happen up to 7 days later when the user got, late event can come up to 7 days later when the user actually saw that event, because again, the app goes into background and whatnot. So, and also these, so because of that, our join window actually expands from hours to days. And storing that large context in native joins or native RocksDB sort of was not comfortable doing that. Okay. So we'll basically jump to just to the end of it, so that I'll talk about what we did. We basically introduced, we used Aerospike to capture both the streams, just the streaming. So what we did was that whenever a serving event is generated, we park that into Aerospike. And whenever a user event comes, it looks into Aerospike. If there is a relevant stream serving metadata present for it, if it's there, it enriches and pushes forward to the aggregate stores or the aggregated processing pipelines, which can run stream aggregation and then render the real-time feedback. This was where we leveraged Aerospike to actually power our stream joins. And this is something which we also scaled up to other pipelines doing this joins on. So that was it. I'll probably close it here. Thank you, guys.